microcontroller to generate these carrier signals. Okay. Once we set them properly or decide them, we keep them fixed. So carrier amplitude, peak value, it will be fixed number. Okay. Modulating signal peak, it is going to be varying in the range of 0 to V modulation triangle peak. I hope this point is clear. Their ratio is a very, very important term. Okay, this V modulation peak is same as this V control peak or whatever, and this V tri peak. This ratio is known as MA. Okay, let me write in simple term. MA. What is MA? It is known as amplitude modulation index. Okay, sometimes this amplitude is not mentioned clearly, sometimes it is known as modulation index, MA. Okay, how do you define MA? It is the ratio of peak modulating signal divided by peak of triangular signal. Okay, it will vary in the range of 0 to 1. Like duty ratio, if you remember, it varies in the range of 0 to 1. Because peak of the modulating signal, it will vary in the range of 0 to V tri peak, isn't it? So that's why modulation index, it should vary 0 to 1. That is the desired range. Okay, we call it linear range. If MA goes beyond 1, it may happen, right? Let's say you have selected during some operator mode, your modulating signal peak goes beyond triangular because it is generated by speed control strategy. So in case your modulating signal peak goes beyond triangle peak, this is known as over modulation zone. So in case modulating signal amplitude goes beyond triangle carrier amplitude, it is known as over modulation zone, and we generally avoid it. Okay, we generally avoid it. How we avoid it? By putting appropriate limiters. Okay, for example, you look, whenever I was showing some closed loop controller, we always keep some limiter here, right? Any PI controller comes with a limiter. So this PI controller effectively generating this modulating signal. So these limiters are designed such a way that, or set such a way that modulating signal remains within 0 to V tri peak. Okay, that is the reason we are using a limiter. Okay, so deliberately we want those modulating signal to be within the triangle carrier peak. That's why this limiter will be used, so that in regular operation the modulating signal does not go beyond carrier signal. Okay, that is the role of the limiters. Of course, you can ask a question, how do we decide this carrier peak value? Those things will come slowly. Okay, as I told, if I design a carrier frequency and carrier amplitude fixed, I am going to keep it fixed. But how do we decide at what value I am going to select them? That I am coming next. Okay. So this modulation index, generally it will be varied between 0 to 1. Simple. Because we want to make it in the linear range. You can ask a question that why it is not beyond more than 1. Sometimes we go more than 1 But problem with more than one is that it introduces more harmonics. Okay, so let me write that. Why we avoid? Because it generates more harmonics. Generally, more harmonics generates more torque ripple. Okay, and also sometimes it generates more losses. So operating in overmodulation zone is generally avoided because it introduces more torque ripple, more losses. That's why we generally avoid going into overmodulation zone. We want to keep inside linear modulation zone where range of MA will be 0 to 1, like the duty ratio we studied in DC-DC converter. Okay. There is one more ratio you can see, MF. So one ratio we have studied, which is modulation index. One more, another important ratio is MF. Okay, I hope you understand the difference between both of them. One is MA, another is MF. MA is amplitude modulation index. So logically, MF is going to be frequency modulation index. Frequency modulation index. Okay, MF. This is given by Fs by F mod. Fs is nothing but your carrier frequency. Okay, and F mod is going to be your modulating signal frequency. So this triangle carrier, whatever you are using, right, that frequency will be Fs, and F modulating signal is the modulating that whatever current you are giving to the motor, that frequency is ultimately decided by modulating signal frequency. So this ratio is known as MF. Okay, it is a customary design or choice to select MF higher than equal to 21. Why? To avoid subharmonics, to avoid need for synchronism, carrier synchronization. Again, these are some hardware topics, you may not get it very clearly. So basically, to allow asynchronous operation also. Okay, so again, these are very hardware dependent things. If time permits, I'll describe. Otherwise, just note that this carrier frequency is generally selected at least 21 times higher than the modulating frequency. Okay, to avoid certain hardware implementation restrictions, and another issue is also there. I'll come to it, but let me take up this first. So you know, MF is ratio of Fs by F modulating signal. Now, if someone asks you, how do you decide Fs? What is Fs? It is ultimately going to be your switching frequency of the switches. It is also going to be the triangular carrier frequency. Okay. So how do you decide that? At least I know it has to be more than 21 times. So Fs has to be greater than or equal to 21 times F mod. Okay, that is coming because of mainly hardware limitation, and also there are other reasons. I'll tell one by one. Now, how do you decide F modulating signal? Is it a constant? Answer is no, right? Because motor speed is directly proportional to F mod. How? If you remember, our synchronous speed is 120 F by P, right? So this motor speed is proportional to this F mod. Basically, F mod decides the power supply frequency that you are giving to the motor, right? Or the current or voltage that you are giving to the motor. That AC frequency depends on F mod, modulating signal frequency. Now, how do you decide motor speed? Do you remember we had some calculations? I gave you homework also. I'm not sure how many of you did it. No one asked any doubt regarding the homework today. So I assume most of you did not do it. In case you did it, you faced some problem, you would have asked me, right? So last week I gave you homework and I don't know whether you did it or not. There has to be some action from your side also, right? I hope you did it. So if you have any doubt, I'll help you. No worry, after this session. So if you know, basically there will be a vehicle maximum speed. For example, let's say you are designing some company XYZ brands, XYZ model. So you have a target in mind that my vehicle maximum speed, let's say X kmph, right? From this you can do back calculation. We already did it in the last week. How to calculate motor speed. How to calculate motor maximum speed. So if I know what is my motor maximum speed, I'll know what is my F modulating max value. I hope this point is very clear, right? So if I know what is my F modulation max value, I'm going to multiply it with 21 at least. So that will be my Fs minimum value. Because I want Fs to be at least 21 times F modulating signal. 21 times F modulating signal is maximum value. So basically at maximum value, if I ensure that my Fs will be more than 21 times, any value less than the maximum value of F mod, switching frequency will be always 21 times higher, right? Very simple math. So from vehicle maximum speed, we know vehicle maximum motor speed requirement, from which I know what will be the maximum frequency of the motor current, from which I'm going to get maximum frequency of the modulating signal. We are going to multiply it with 21 to give me minimum carrier frequency, okay? So this is the minimum carrier frequency, right? Maximum carrier frequency is infinite. But then you know any physical switching device you are going to select, be it MOSFET, be it IGBT, they have a practical switching frequency limitation, right? For example, we discussed earlier, IGBT is generally preferred in a range of maximum switching frequency, let's say 15 kilohertz, 20, 25, in that zone. MOSFET, you can use 100 kilohertz, 200 kilohertz also, right? Nowadays, wide band gap semiconductor devices, silicon carbide MOSFET, GaN MOSFET, right? Those can be, some of them can be operated at 500 kilohertz, 1 megahertz also, right? But then everyone will have their own maximum limitation. Okay, so minimum limitation of switching frequency coming from vehicle speed requirement, motor speed requirement and all, and maximum speed switching frequency limitation will come from physical device constraint. Typically, in a motor controller, okay, there is not much benefit of going for a very high switching frequency. I repeat, in a motor controller, there is not much benefit of increasing switching frequency. You can ask why? Because you see in the motor controller output, there is no additional inductor, no additional capacitor we are using, okay? So let me repeat that part. In a DC-DC converter, if you remember, at the output side, we had some capacitor, we have some inductor, if you remember, right? But you see at the inverter output, we generally don't use any filter element. So that is the contrast difference between DC-DC and DC-to-AC converter. Let me repeat. See, this is a DC-DC converter, okay? It will have a most practical implication, there will be a capacitor here. So this inductor capacitor, this size is proportional or at least to F, sometimes it is F square also, okay? So switching frequency if you increase, sorry, it is 1 by, my mistake. So switching frequency if you increase, size comes down. That is the reason that we generally go for higher switching frequency. But here you see at the output of the inverter, this is nothing but your motor inside it. There is no additional filter in general. Okay? No additional LC. I hope you can see the difference, right? So that's why there is not much benefit of going at much higher switching frequency, because there is no additional LC. So their size was not a problem because there is no additional LC filter at the output side. So size benefit for going higher switching frequency is not that severe, right? Size of this capacitor actually depends more or less at the motor frequency or your energy calculations. So not much on FS. Okay, I repeat, this capacitor, one capacitor is there at the inverter input side, but its size selection does not depend much on the switching frequency. So there is not much benefit of increasing switching frequency to a very high value. That's why you see motor controller generally will be operated in a moderate kind of switching frequency, because it has to be at least 21 times higher than motor frequency, right? Just take an example. Let's say if you are selecting a motor of fundamental frequency, let's say 100 Hertz. Okay, so that means your synchronous speed will be 120 F, 120 into 100 by P. P is number of pole. So now minimum pole you can have is 2, right? So in any magnet system, minimum pole is 2. So if you go with 100 Hertz frequency, the speed you can go is this will be 50. So 005 plus this RPM. Okay. So what I'm trying to say is, if you just go with regular 100 Hertz frequency for the motor, the NS, the speed of the motor effectively will be 6000 RPM. So if you go with 100 Hertz as your motor fundamental frequency, then your FS, if you can make it 21 into 100, that means 2.1 kilohertz. That is good enough. So typically, you see that the motor controller in EVs, they will be having switching frequency in the range of 10, 20 kilo or something like that, not much higher, typically, okay? Because if you go with very high switching frequency, your losses increases, switching losses increases. Whereas for a DC-DC converter, typical switching frequency will be somewhere around 50 kilohertz, 100 kilohertz. These are common, very common choice. Okay, I hope you got some idea, right? So this switching frequency of that switching frequency of the MOSFET IGBT, that will depend on your carrier frequency, and typically 10-20 kilohertz is quite a good choice. But again, you have to do a lot of calculation to find out the optimal choice. But typically it will be around this zone. Okay. So this is about how do you decide carrier frequency. Okay. Now, quickly I'll talk about carrier peak amplitude. How do you decide? And then I'll take up your questions. So first I discussed how do you decide FS, right? Next, let me talk about how to decide that triangle carrier peak value. Okay, so we try peak. How do you decide? So this is this carrier signal, as I told earlier, it is implemented inside a microcontroller. How? Generally, it is implemented by a counter for simplicity and understanding. Counter, okay? This comes under the subject called digital electronics. Okay. So what does a counter do? Counter basically is a digital device right? It keeps on counting the numbers, as the name suggests. It keeps on counting, and whatever, when your counting is over, it just resets. Okay, and then again it starts counting. So this is how a counter works. Okay, so this kind of counter is known as up counter. Similarly, this kind of counter, I hope you understand, these are nothing but some steps, right? It every time it increase the count by 1, then again zero. So this is basically up down counter. All right. So for simplicity, basically, let's say I have a, let's say I am using a, how many count? 1, 2, 3, 4, 5, 6, 7. Let's say this is a 7 count. Okay. So for 7 count, how much time I need? This will be 7 into clock period of that microcontroller. So microcontroller, it will have its own counter. So that count clock period, basically this for one increment, that will be the small time period, that is your T clock. Okay. So for one small increment, microcontroller needs some time, right? So that generally will be derived from clock frequency of the microcontroller, or there may be some scalar multiplication, right, with the frequency. So basically, microcontroller, inside that there will be crystal oscillator, and based on that crystal oscillator, you can also use some pre-scalar or post-scalar. What I mean is, basically inside every microcontroller there will be crystal oscillator which creates this pulse of some frequency. Okay, so you can use some pre-scalar or post-scalar. Basically, you can use some sort of factor to this frequency. Let's say your crystal oscillator in a microcontroller generates 1 megahertz. But you need a 10 megahertz signal. So you can use a post-scalar of 10 times. So these are again some arrangement available in the microcontroller. So for simplicity, let us forget about it. Let's say I have a crystal oscillator in the microcontroller which is generating just a simple square pulse of 1 megahertz. Okay. So then in my counter, to have one count, I need that one frequency, basically. So that will be 1 by 1 megahertz. 1 megahertz is the switching frequency. So your T clock will be TLK will be 1 by 1 megahertz. It's very tiny time, isn't it? So now I hope you understand that if I want to, let's say simplicity, if I want to get a sawtooth signal from my calculation in previous slide or somewhere, let's say we have decided this one. So let's say we finalized based on several calculation, etc. Let's say it is 15 kilohertz. So that means your TS is going to be 1 by 15,000 second. Okay. So what is your time period for the carrier signal? 1 by 15,000. So this time period you want 1 by 15,000. Okay. So this got fixed because carrier frequency will get fixed, right? So then from this you can find out what will be your counter value. Counter value. How? So see, this time is counter value into clock period. So this is nothing but this switching frequency, and 1 by switching frequency is your carrier frequency. So this is nothing but your carrier frequency. So that will be given by T clock of the microcontroller into